Hello, today we are going to look at 4.1 Day 2, determining local extrema and inflection points using algebra. So we're going to expand what we learned yesterday to what we're going to do today. So today's objective is I can use derivatives and sign charts to determine where local extrema are located and intervals of concavity. So the first thing I want to say is local extrema is just max and mins. Okay, so a new word for local max and local mins. So we are going to be given functions and we're going to be able to find their critical numbers, determine whether our functions have local max or mins. We're going to figure out where our function's increasing or decreasing. We're going to figure out where our inflection points are and if our intervals are concave up or concave down on our function. Okay, so let's just start off with f of x equals x to the fourth minus 18x squared. I want to find critical numbers of f. So these are the places where my first derivative equals 0. So remember yesterday when we were talking about critical numbers, we were talking about the slope of the tangent line being 0, and that meant it was going to be a max or a min. Well, the slope of the tangent line, as we remember, is just the derivative. So we go ahead now and just take our derivative using our power rule, and we set it equal to 0. And then we just solve for x. So I'm going to go ahead and factor out a x and a 4. That's going to leave me with x squared minus 9. And then I'm going to factor some more, because this happens to be the difference of squares. And I'm going to see the places where this function will equal 0. It'll equal 0 when 4x equals 0, when x minus 3 equals 0, and x plus 3 equals 0. So 4x equals 0, one critical point will be at x equals 0. If x minus 3 equals 0, then x equals 3 will be a critical point. And if x plus 3 equals 0, then x has to be equal to a negative 3. So my three critical points are 0, 3, and negative 3. Now we want to determine if these points are local mins or local maxes. And to be honest with you, I usually do C before I do B. Because C tells me where my function's increasing or decreasing. And so I do a sign chart. I break up my whole real line using my three critical numbers, -3, 0, and +3. Now I want to warn you, sign charts are not graded on AP exam, so they're not considered justification. You have to write sentences for justification. All right, but we use it a lot to show our work, and then we can explain our work later. So I have my derivative, which I know is, I'm going to just write it right here. So 4x times x minus 3, x plus 3. This is my derivative. And now what I'm going to do with my sign chart is I'm going to pick a number between negative infinity and negative 3. So maybe I pick negative 100. And I'm going to stick negative 100 in everywhere I see an x. So I have 4 times a negative 100, which is equal to negative 400. So that's a negative number. And then if I put a negative 100 there, negative 100 minus 3 is also a negative number. And then if I put a negative 100 there, plus 3 is a negative number again, negative 97, right? So we have three negative numbers multiplied together will result in a negative number. Okay, I don't really care what the number is, I just care if it's positive or negative. Okay, so then I'm going to pick a number between negative 3 and 0. So say negative 1. 4 times negative 1, so now I replace it and I'm just looking at negative 1. So 4 times negative 1 is negative. Negative 1 minus 3 is negative. But negative 1 plus 3 is positive. And if I take a negative number times a negative number times a positive number, I end up with a positive number. All right, then I pick a number between 0 and 3, so let's say 1. Okay, and so now I'm going to make these all positive ones. So 4 times 1 is positive. 1 minus 3 is negative. 1 plus 3 is positive. And a positive times a positive results in a negative. And lastly, I pick a number between 3 and infinity, so 1002. All right. If I pick that number, I end up with 4 times 1002, which is positive, 1002 minus 3, which is positive, and 1002 plus 3, which is positive. And 3 positive numbers multiplied together gives me a positive number. So now I have a sign chart on my derivative. So this was my derivative sign chart. And if I know if my derivative is positive, I know my function's increasing. So I can answer C now by saying, okay, well, from negative 3 to 0 and from 3 to infinity, my function is increasing because my derivative is positive. All right, and similarly, I can say from negative infinity to negative 3, and from 0 to 3, my function must be decreasing because my derivative is negative. All right, and then C helps me answer my local min and local max. Using my sign chart, I can say, okay, well here, if my function went from negative, so my function went from decreasing, since the first derivative's negative, so it went from decreasing, and then at negative 3, it turned increasing, then I know that negative 3 is a local min. And my justification is because f prime switched from negative to positive. All right. Similarly, I can say at 0, right? So my function had been increasing from negative 3 to 0, but then at 0, my function will, after 0, starts to decrease. So you can see that x equals 0 is a local max. And your justification is because f prime switched from positive now, it was increasing function, and then it went to a decreasing function. And now check negative 3, so we were decreasing from 0 to 3, but then after 3 it started increasing. So then you can see that 3 is also a local min because the first derivative switched from negative to positive. All right, now let's move along to the second derivative. Now my calculator is not working online, so I can't show you this right now, but it would be a good time to just put this equation into your calculator and make sure that our work matches what our calculator says. All right, let's look at E. Find the inflection points of F. All right, so our inflection points, as we learned yesterday, deals with the second derivative. And our second derivative of this function is going to be 12x squared minus 36. Remember, we have the first derivative right there, so the second derivative, we just use the power rule. Now our inflection points don't happen when our second derivative equals 0. It happens when our second derivative switches signs. But the only way to figure out when it switches signs is to figure out where does it first equal 0. So the first thing we're going to do is just take our second derivative and set it equal to 0. Just like the last one, I'm going to factor out the 12. And then I'm going to factor this as the difference of squares. It's a little tricky to see that it's the difference of squares, but you take the square root of the first number, which is x. You take the square root of the second number, which is just the square root of 3. And so it's x minus the square root of 3, x plus the square root of 3. And so then you set each piece equal to 0. Well, 12 never equals 0, so there's no inflection point possible there. So then the square root, x minus the square root of 3 will equal 0 if x equals positive root 3, and x plus root 3 will equal 0 if x equals negative root 3. So these are our possible inflection points. but we can't say their inflection points yet until we determine if the second derivative actually switch signs. So I actually, again, like to do the sign chart first. So I do the f first here. Okay, keep in mind my second derivative is equal to 12, x minus the square root of 3, x plus the square root of 3. And just like we did for the first derivative, I break up the whole real line using my two possible inflection points. So the positive square root of 3 and the negative square root of 3. Of course, we want to stay with the whole real line. So this is negative infinity to negative root 3. So we pick numbers between negative infinity and negative root 3. So let's say negative 500. If I put negative 500 in there, I will see that I have a negative 500 minus, so that's going to be a negative number. And then I have a negative 500 plus root 3. Well, root 3 is only like 1.7, so it's still going to be negative. And two negatives together make a positive. All right, then I pick a number between negative and positive root 3, 0. So 12 is always positive, so we don't have to worry about it. So we do 0 minus root 3, which is minus, or negative, and 0 plus root 3, which is positive. And a negative times a positive will result in a negative number. And then lastly, we look at a number greater than root 3, say, 10. Put 10 in there, we have a positive number, 10 minus root 3, and another positive number, 10 plus root 3. And a positive times a positive makes a positive. So now we can say our function, because remember the second derivative tells us all about concavity. So our function is concave down on the intervals where, I'm just going to put on negative root 3 to positive root 3, because my second derivative is negative and our function is concave up wherever my second derivative is positive. So on the interval from negative infinity to negative root 3, union root 3 to positive infinity, and that's because our second derivative is positive. Okay, brings us back to unit 3 or 2 way back when. All right, here's another example. Why don't we take a look at this and try it on your own. Okay, so let's see how you did here. So finding your critical numbers, you took your derivative, you set it equal to 0, and you ended up with negative 3/2. Okay, check to make sure that works out for you. All right, then we determine if our critical numbers are a local min or a local max. Well, there's only one, so we break up the whole real line from negative infinity to positive infinity, and we have negative 3/2 there. We're putting our test values, so say I test out negative 23, and I put it back into my derivative. Remember, my derivative's right here, so if I do 4 times negative 23 plus 6, I'm going to end up with a negative number. And then if I pick a really large number, so 1 million, and 30, I don't know, something random. And I put that number in there. 4 times that number is going to be huge, plus 6 is still going to be positive, so you're going to end up with a positive. So you can tell me that because your derivative switched from negative to positive, that meant your function was decreasing and then increasing, that at negative 3/2 we are going to have a local minimum. And this should make sense with what we know about this, because this is a happy parabola, right? It's a parabola that opens up, and so we know that the vertex here is going to be a minimum. All right, then if we go to C here and find the intervals where f is increasing and decreasing, again, we've done the sign chart, so we can kind of use that now. So we can say our function is decreasing on this interval where it's negative, negative infinity to negative 3, because the first derivative is less than 0. And we know our function is increasing when our first derivative is positive. So we can see that's happening from -3/2 to infinity. All right, now take a minute and do the second derivative and find me points of inflection. All right, if you're back and ready to see what we did, so we did the second derivative, which is interesting because our second derivative is just 4. And so we'd take our second derivative and set it equals 0, but 4 will never equal 0. So this means there are no inflection points on this, which means our function doesn't switch concavity. And to figure out where it's concave up or concave down, we know that the second derivative is equal to 4, which is always greater than 0. So therefore, everywhere, f has to be concave up. So, and again, if we think about our happy parabola, we can see, oh yeah, it is concave up everywhere. So that matches with our intuition. All right, I just want to go back real quick and talk about the inflection points because I don't think I justified on the last example. And I just wanted to double check because this is always something people mess up. All right, just because your second derivative equals 0 does not mean they're inflection points. These are inflection points because the second derivative switch signs. So x is equal to the square root of 3 and the negative square root of 3 are inflection points because the second derivative switched signs. We don't really care that it switches from positive to negative or negative to positive like we do if it's a local max or a local min, but it just has to switch signs. And so you have to make sure that when you're looking for inflection points, you always double check. Did the second derivative actually switch signs where it was equal to 0? Because you can see that there are places, like if this was, it didn't switch signs here, so that wouldn't be an inflection point. All right, hopefully that's helpful. There's one more example that you can look at if you need to. It's got the product rule in for the derivative. Take a look at that if you need to. Otherwise, go ahead and get started with the work. Thank you.